Today, exam 7 on chapter 13, gases, is due by midnight. And since there's nobody in seat to take the exam, I'm going to start on introducing material for chapter 16, which is acids and bases. Actually, it should be acids, bases, and pH. They all go together. Right. So this is out of the way. And we're on to chapter 16. I found a deficiency in the textbook and the way things are presented. And since we don't cover chapter 17 explicitly in this course, there are certain topics in chapter 17 that will make chapter 16 more understandable. So I'm gonna pull out some information from chapter 17 on equilibrium and describe that first so that chapter 16 will make more sense. So let's look at some of the chapter 17 material. Chapter 17 on equilibrium. Well, first of all, what do we mean by equilibrium? Well, the word itself should invoke an idea of something's equal to something else. And in fact, in chemistry, equilibrium, at least as far as I can tell, is based upon the rate of processes. So in our example here, we have a liquid that is, we place a liquid in a container. This is an Erlenmeyer flask. Right? So we put a liquid in here that has whatever degree of volatility you choose. Some can be more volatile than others, but the concept still works no matter what liquid we put in there. So now we've got this liquid in here and it's open to the outside. Well, we want to close this system off. Right? So there's your stopper. And now we've got liquid in here and only air in this space. But immediately, molecules start leaving the surface of this liquid. And they start accumulating in the head space. Okay? In the beginning, this is a one-way process, right? It just goes that way, and that's it. But as the concentration of vapor builds up, the vapor that's produced from this liquid, you start to get return. So some of these go back. And on the microscopic level, this is happening continuously. We've got evaporation and condensation happening at the same time. And what you'll notice from the outside, observing the liquid, is the volume will probably drop. Sometimes it'll drop a lot, sometimes just a little bit. But that just shows that some of that liquid is being turned into gas. Okay. Equilibrium is reached when the rate of evaporation equals the rate of condensation. And what we observe is that the level of the liquid stops changing. It doesn't get higher, it doesn't get lower, it stops. So the equality here is between the two processes, evaporation and condensation. The rate of one equals the rate of the other. So that's your balance. Now, this is a physical process where we evaporate and condense. We can apply this same concept to chemistry as well. So when you get a reaction that, say, let me try to think of a good reaction. Most of the reactions that come to mind right now are largely one way. I was trying to think of one that was equal in both directions. One will come up in the subsequent slides. So this is known as a dynamic state. It looks static from the outside. We don't see any change at equilibrium. But on the microscopic level, the activity is furious. Evaporation condensation is happening at enormous rates, but the balance is what's important. And we quantify these rates in terms of concentration. In other words, how is the concentration changing? Concentration here is changing at a certain rate. Concentration up here is changing at a certain rate. And that's where the balance is in terms of our calculations. And I'm going to show you that in just a second. Now, there's a principle in chemistry where we have, let's just speak of this in terms of generics. Say we have some chemical A and some B, and it produces two other products. All right? So it can go this direction. And when you get enough of this, say we start off with A and B only, then you produce some C and D. Once you get some C and D, it's entirely possible, and the degree that at which this happens depends on the reaction itself. So once you get some products built up, they have the opportunity to return to reactants. So you get this balance, a rate going this direction, a rate going that direction. And that's a balance. Well, what Le Chatelier says is that once you have reached equilibrium and the rate of the forward equals the rate of the reverse, anything you do to disturb that equilibrium will elicit a response from the system in such a way as to minimize the stress. So if we stress the system, and let's say the simplest way to stress the system is say, once it's in equilibrium, add some A. If we add A, now we have more opportunity for A to interact with what B is left, and we get an increase in the forward rate. So as that increases, it produces more C and D, and now the reverse rate increases. And that process continues until you reestablish the balance. So the system responds to mitigate the stress. Right, so this is your stress. There are a couple of other types of stresses, and we can talk about those later. So here's an example. Yeah, this is a good example. So if we have water reacted with carbon monoxide, and they're both gases, they're in the vapor phase, and we produce hydrogen gas and carbon dioxide gas. Okay? So once we've established equilibrium, and we have some reactants and we have some products, and the forward rate equals the reverse rate, what happens if we add water? If we add more water vapor, then the chances of water encountering a carbon monoxide molecule and reacting with it increase. So we increase this value, this amount, it reacts with the carbon monoxide that remains, produces more hydrogen and carbon dioxide, and now they return rate, and we reestablish equilibrium. What if we add more hydrogen? Right? Instead of adding water, now we're at equilibrium again. What if we add this one? Now we have the possibility of hydrogen encountering more hydrogens encountering carbon dioxide and returning to the reactant side until the rates are equal again. So that shift is the way the system reacts to mitigate the stress. We have stressed the system by adding hydrogen. Okay. What you see here in this slide is called the law of mass action. And it's a way of quantifying the equilibrium status of any reaction. What we need is to take into account concentrations, and that's what the square brackets mean. Square brackets mean concentration at equilibrium. Okay. So the concentration of product C and the concentration of product D are placed in the numerator, and they multiply by each other. But also, their concentrations are taken to the power of their coefficients. So in this example, K is a constant, and sometimes we write KEQ to distinguish it from any other K. K usually means constant. Then in our example here, we would have hydrogen concentration to the first power and carbon dioxide concentration to the first power in the numerator. And in the denominator, we would have water to the first power and carbon monoxide to the first power. Now, this expression is a constant for that reaction, but it's only constant for a given temperature. If the temperature changes, the constant changes. And this is known as the equilibrium constant. Now, these subscripts, some of them we have reserved for particular types of equilibria that we discuss. For instance, Ka is the constant for acid dissociation or acid ionization. We'll talk about that one as soon as we get out of chapter 17. KEQ is a generic. Okay. KW is reserved for water. Pure water undergoes a reaction that we're going to discuss. And this particular K is reserved for that reaction. There are others like KF is the constant for formation of a complex ion. And let's see, there was one other one I was trying to think of. KSP is solubility product, right? We haven't talked about that, I don't believe. But the subscripts mean something specific. And if you see one of those, then it gives you an idea of what that K refers to. Okay, so here's another example. This example of chemical equilibrium is the Haber-Bosch process, where we take nitrogen, combine it with hydrogen, and make ammonia. Notice that there's only one product, ammonia, and it has a coefficient of 2. So the ammonia in square brackets is raised to the second power, it's squared. And then in the denominator, we have nitrogen to the first power and hydrogen to the third power. And that's the expression for the equilibrium constant for that equation. Now, there's a difference between the equilibrium constant and the equilibrium position. Let's see. Equilibrium constant and the equilibrium position. Okay? The equilibrium constant is just that. It is a constant for a given temperature for any reaction that we choose to describe in that way. The equilibrium position, on the other hand, can vary for any reaction depending on its starting conditions or any stress that's applied to it after it reaches equilibrium. So this is a constant. The position can change. It depends on concentrations and where the equilibrium stops. That's the equilibrium position. So you can have different concentrations of the reactants and products. And once you put them in the expression, you get the same constant. But you can have different concentrations to get you to that position, to that constant. Okay, that's what we mean by the difference between position versus constant. Okay, so let's consider this particular reaction. This is acetic acid. Okay. We would write acetic acid this way, C2H3O2. And we know it's an acid because it's an aqueous solution. It has a hydrogen out here by itself. And what it does is in aqueous solution, it ionizes and produces that hydrogen ion plus what's left over, the acetate ion. Okay? And that equation is balanced. Now, how would we write the K? The equilibrium constant for this expression is simply Ka for acid. We have an acid ionization, so we use a subscript of A. We would have the hydrogen ion concentration times the acetate ion concentration divided by the undissociated acid. And they all have coefficients of 1, so everything's taken to the first power. Now, this particular expression appears in that one right there. That would be the equilibrium constant expression for this acid ionization. Here we go. Okay. Let's actually do a calculation. Dinitrogen tetroxide decomposes into 2 nitrogen dioxide. Okay? What's the expression for that one? Well, the equilibrium expression for this one would be NO2 squared, because of that, divided by N2O4. Okay? So if we know those values at equilibrium, we can calculate the constant. And in this case, we do know what they are. They're given to us, 0.055 molar. That's in the denominator. Numerator is 0.060, 0.060 molar squared divided by 0.055. Okay. Now I'll point one thing out. I may have a slide on it. I don't recall. We don't put the units of measure in here or in our in the K value because the complications that arise when you have multiplications of numerous different units of measure taken to a power, the unit of measure of K can be anything. So what we do is we only quote the number, and we're very careful about how we construct it. Right? We can't depend on the units of measure in this case. So let me get my calculator. And we'll determine what that value is, 0.060, and I'm going to square that and divide it by 0.055. And I get two significant figures, 6.5 times 10 to the minus 2. Oh, in standard notation, two places to the left, 0.065. There we go. That would be our K value. I may have a slide on this, but I'm going to make a point right now. In this expression, the equilibrium expression, this mass action, the law of mass action, we include terms from our equation that can change concentration. Gases, yes. You can have so many moles per liter. Right? That's a concentration. However, if you have a solid, there's no way the solid concentration doesn't change, because if you react a solid with something else, then as you lose solid, the volume decreases and you lose moles. So moles per liter makes no sense. We just leave solids out of the calculation. They're not entered in anywhere in here. Also, pure liquids. Okay? Pure liquids do not enter in. So if we had water in the liquid state or the solid state, either one, that term would not be included in the equilibrium expression. So solids, pure liquids are kept out. The only thing we put in here would be gases, aqueous solutions, or any other type of solution that can change concentration. Okay, now back to the slide. If the value of K is much larger than 1, what does that mean? If this value is, if the K for any reaction is larger than 1, let's go back to our generic. All right, so we have C to the little c, D to the little d, over A, little a, and B, little b. What does that mean when this is a very large number, greater than 1? That means that the equilibrium state, or the position of any reaction, reaction pertaining to A plus B equals C plus D, that means that the position of the reaction at equilibrium is far to the right, as written. Remember, if you say a change in a reaction is right or left, you must refer to a balanced equation, because we can flip that equation just as easily, right? If it's going one way and it can go the other way, we can flip it. It still goes one way or the other way. But if you flip it, then the equilibrium change is different. It's opposite. So a balanced equation is essential if you're going to say the position moves left or right. Okay, so if it's greater than 1, that means the products are favored because this is very large and that's very small. And as written, it moves to the right. If the K is very small, then we have very little product and a lot of reactant left. And that means the left-hand side of the equation as written is preferred. Now, what does that mean? Say this is K is much, much less than 1. Then what if we flip the equation? Then what would K be? We would invert the K to the -1, be much, much greater than 1. Right? If we flip the equation, now the products are favored because they used to be reactants. See how that works? All right. So if the equilibrium lies to the right, the value of K is large, greater than 1. And if it lies to the left, we have a small K. All right. So that's the part of chapter 17 that I want to present to you. And you can go into 17 and find those sections that we discussed if you need some more reading. And now we're going to get back into chapter 16 and talk about acids and bases. With this concept of equilibrium firmly established, we can use it to understand acids and bases. All right. So, what do we mean by an acid or a base? Well, initially, we used our senses to determine what's an acid and what's a base. Acids, if it's safe to taste them, there's a danger if you don't know the concentration or the degree of dissociation. You could taste an acid and damage your tongue. But typically, if they're safe to taste, an acid will be sour. Okay? And likewise, if we taste a base is going to be bitter. Right? So they selectively stimulate the different parts of your tongue that give you these sensations. Okay. By the way, if you've ever taken medication and it's encapsulated and you accidentally bite it, more than likely, not always, but more than likely, it will taste bitter because most medications are basic in nature. Not all, but a considerable number of them are. Okay, now let's look at the chemistry definition for acids and bases. The first one that we want to discuss is proposed by a scientist named Arrhenius. I think he was, Arrhenius was Danish, I think, or maybe he was Swedish. Difficult to remember. Arrhenius' definition simply said that an acid is a molecule that has a hydrogen available to ionize. So when you put it in aqueous solution, some of those hydrogens leave the molecule and they become available to give you the sour sensation or to do any type of reaction involving hydrogen ions. So this would be, let's separate them just a little bit. Our equilibrium expression then would produce hydrogen ions plus what's left over. Arrhenius said that a base is a molecule that has hydroxyl ions in its composition, like that. So when we put that one in solution, it produces that molecule, the cation, plus hydroxyl ions. That was Arrhenius' definition. And for a great many reactions, that's perfectly fine. It works. However, in defining the reactivity of acids and bases, we find that there are some molecules that, particularly bases, that do not have hydroxyls in their makeup, but they still produce the same type of solution that you would expect from a traditional Arrhenius base. Examples. Ammonia in aqueous solution produces hydroxyls. All right. How does it do that? Well, it took a little while, but we finally figured it out. In aqueous solution, water is a reactant. Water reacts with ammonia, and it sets up an equilibrium that produces ammonium ions plus hydroxyl ions. Okay? So Arrhenius' definition doesn't fit for that one. So here's what we have to do. We have to modify our model for acids and bases. And that was done by two scientists independently of each other, so they both get credit. Bronsted and Lowry. Bronsted, I think, was Danish. Bronsted and Lowry was English. Their model doesn't talk about hydroxyls at all. It only discusses acids and bases in terms of hydrogens. So for Bronsted and Lowry, an acid is a proton donor. All right. So how would that work in water? In water, you would have the acid, and it would donate a proton to water. It would leave behind that part of the molecule, and this hydrogen ion would attach itself to water and produce the hydronium ion. This is the correct chemical definition of an acid, because hydrogen ions never exists independently in solution. They're always transferred from one place to another. They're always donated or received. And that brings us to the base. The base is a proton acceptor. So if we have a base of any kind reacting with water, then that base accepts a proton from water and leaves behind a hydroxyl. Okay? And there's your example. And this definition covers all the Arrhenius acids and bases plus others that don't fit the Arrhenius definition. Okay. Oh, by the way, in the Bronsted-Lowry definition, this is an acid because it's a proton donor. It's a hydrogen donor. That makes water a base because the base accepts a proton and makes this one. Okay. What does that make this? Well, in terminology, this is a conjugate base because now it is able to accept a proton. This is a conjugate acid because it can donate that proton. So going back this direction, that acid donates a proton to this base and makes this acid in this base. All right, so the forward reaction, reverse reaction are defined here. All right, that's what happens to a generic acid in aqueous solution. Now, one thing you'll notice is that the conjugate base of an acid has only lost one proton. If it loses more than one proton, it's not the conjugate base. We take these reactions one proton at a time. So if your acid happens to have two protons, like that, the conjugate base would be this one plus the hydrogen. And then that one can undergo a second reaction to produce the this conjugate base. So whenever we talk about acid reactions, where we put an acid in solution, we do it one proton at a time because this will have a K value for the first proton, and this one will have a K value for the second proton. Okay. Our example here is hydrochloric acid. Hydrochloric acid is a strong acid. In other words, the HCl essentially gives up all of its protons. So the reaction is essentially all the way to the right as written. Okay. And there's your polyatomic ion, the hydronium ion. Okay, let's see if we can make sense of these in terms of Bronsted and Lowry and define a conjugate acid-base pair. All right, A, B, C, and D. The first one, HCl and HNO3. In aqueous solution, those two are both acids. They have no relationship to one another in terms of conjugates, right? So that's not it. The second one is this one and this one. Okay. Is that possible? Well, yeah, but it happens in two steps. What's left over after you lose one proton here? Just water, right? Water and the other proton, which would be transferred to something else. And then this one would produce that. So the conjugate acid-base pair here is this one and that one, or this one and that one. That's not what we have there. Right? So that's not it. How about C? H2, SO4, and SO4, 2 minus. Right? You'll recognize this one in aqueous solution as sulfuric acid, but it's got two acidic protons. If it gives up one of them, you're not going to have that. You're going to have this. So, as given, that's not it. How about this one? There you go. If we wrote out the complete reaction, and this is an aqueous solution, it's reacting with a water molecule. It's in equilibrium with lose one proton, we get Cn minus plus our hydronium. There's your acid-base pair. Acid conjugate base. That's the one right there. Okay. I mentioned strong acid in reference to hydrochloric acid, HCl. In a common understanding of strong versus weak in terms of acids and bases is that the strong acid will cause damage if you get it on your skin. A better term for that would be corrosive, and that's what what OSHA, Occupational Safety and Health Administration, and the EPA define as corrosive. But in chemistry, chemical terms, a strong acid is defined by the degree of dissociation. So an acid that ionizes completely, it completely dissociates, is considered a strong acid. And it can be in a very low concentration or very high concentration. Its degree of dissociation is virtually complete, either way. Now, the high concentration will cause damage. It's corrosive. But the very low concentration won't cause any damage. But they're both the same acid, and they're both strong acids. Okay? That's what we mean by strong in chemistry. A weak acid, on the other hand, provides an undissociated molecule, acid molecule, with very little hydrogen ions being removed from the molecule. Right? So the equilibrium lies essentially to the left. Now, you will get some dissociation, but not much. That is a weak acid. Now, if that weak acid is highly concentrated, such as acetic acid, you can get acetic acid 100%. It's called glacial acetic acid. That is extremely corrosive. You don't want to get any of that on your skin. It will eat a hole in your skin. It will damage you. But it's still a weak acid in chemical terms. The concentration determines how corrosive it is. All right. So this is the author's idea of an explanation. Strong acids are essentially all hydrogen ions and conjugate base. And those hydrogen, we do this for convenience, recognizing that when we say this, we actually mean that. But for calculation purposes, this works just fine. It works okay. Now, for weak acids, you're essentially still mostly undissociated, unionized acid. All right. And this is what I was saying earlier, the difference between strong acid and weak acid. But with a twist. If you have a strong acid like this one, acid. Now I'm going to use an abbreviated form, right? This is not the true chemistry, but this is useful. Recognizing that we actually had a reaction with water. But for simplicity's sake, HCl ionizes to produce hydrogen ions and chloride ions. This is essentially to the right. Right? So what does that mean? If this is a strong acid, what does that say about the base? Well, if it's strong acid, it wants to release those hydrogen ions and go over here. Does it want to come back? No. That makes it a very weak base. A weak base is a very poor acceptor of hydrogen ions. So this is true for any acid in the catalog. Strong acids make weak conjugate bases. And by the same token, a weak acid, like acetic acid, makes a very strong base. This is a weak acid. The conjugate base is very strong because the equilibrium lies to this side. It wants that proton from someplace. Okay. For a strong acid, the forward reaction dominates. As long as we're talking about a forward reaction of the unionized acid to its conjugate base. That's the forward reaction. And for a strong acid, the products are favored. And the reverse reaction for a weak acid is favored. All right. So these are some common strong acids. Let's see here. Make some room. Common strong acid. The slide's going to tell us. H2SO4. Sulfuric acid, H2SO4 in aqueous solution is a strong acid. I'll say something about that in just a minute. Hydrochloric acid is strong. Nitric acid is strong. Perchloric acid is extremely strong. And remember our nomenclature, when we're naming acids, if there is oxygen in the molecule, we don't say hydro. So sulfuric, nitric, perchloric, they all have oxygens, so we don't say hydro. But HCl has no oxygen, so we start that name with hydro. And we take hydrogen chloride, the ide becomes ic, that's hydrochloric. Okay. Now, I will say a word about sulfuric acid. There. That is the strong acid. The first dissociation of hydrogen, ionization of hydrogen from this molecule produces this being a strong acid and a weak base. But the second hydrogen, the second part of the molecule, which can dissociate also, SO4 minus, can produce this plus this, right? This now is a weak acid. And this becomes a strong conjugate base. Okay, think about it. This is a neutral atom, and it's willing to give up a hydrogen ion readily. So that makes it a strong acid. But this conjugate base now is charged. And you can reason that the removal of a positive charge from an already negative charge is going to be more difficult. Trying to extract a positive hydrogen ion from that negative is going to be more difficult. So that's why this is a weak acid, and that's a strong base. And this is true for any polyatomic acid. Phosphoric acid, actually phosphoric acid is weak for all three hydrogens. Okay. These are known as oxyacids. In other words, where the conjugate base part of the molecule has oxygen in it. So H2SO4, HNO3, those are strong acids. H3BO3 is boric acid, it's weak. H3PO4 is also weak for their first protons. So that means all of their protons are weak. All of their acid forms are weak. An organic acid has carbon and hydrogen in the molecule. So the backbone, this part of the molecule right here, this is organic. And not to go into too much detail, but organic always has carbon and hydrogen. And sometimes it has oxygen, nitrogen, sulfur, and some other things. But it always has carbon and hydrogen in it. And in this case, what we're looking at here is the acetate ion. This would be negative, and this would be equal to C2H3O2. Oops, sorry. This is, excuse me. There. That's the acetate ion. Okay. And this is all organic in here, carbon and hydrogen. That's an organic acid. And the release of the hydrogen is from this carboxyl group, the carboxylic acid group. And these acids are typically weak. Lactic acid is another example. Formic acid is an example. Citric acid, these are all organic acids. And they're all weak, as a matter of fact. Okay. Um, all right, that's enough said about that. Oh, a word about safety. If you have a concentrated organic acid, like acetic acid, for instance, 100% glacial acetic acid, where do you store it in your laboratory? Store it. You do not store it with other strong acids that have oxygen in them, like sulfuric acid. Let's see. Acetic acid, glacial, acetic acid, sulfuric, nitric, perchloric. Do not store glacial acetic acid with those. If they come into combination with, if they come into contact with one another, you get a violent decomposition reaction that produces a lot of heat and can produce fire because organics will burn. So keep those separate from one another. Now, the weak organic acids are not quite as big a problem. Phosphoric acid in a concentrated state, yes, it would be a problem. So you want that one out also. Uric acid, right? This is an organic acid that we find in, we have some in our bodies. We don't want too much of it because accumulation of uric acid, particularly in the joints, causes gout. But uric acid is produced in plentiful amounts by some reptiles and all birds. It's the way that they get rid of nitrogen waste from decomposition of nucleic acids and proteins. They combine it into this form because it's solid. And that way, they don't have to carry a lot of water around with them to dilute it like we do with urea. All right. So consider a 1 molar solution of HCl. One molar hydrochloric acid. Let's put these in order, strongest to weakest base. So if we have a solution of hydrogen chloride, hydrochloric acid, it reacts with water to produce, well, let's keep them in, the chloride ion and the hydronium ion. Okay. What can we say about this reaction? Well, we know this is strong. We know that this is a weak base. This is a strong acid. This is, I'll tell you, this one is a weak, since this is an acid, this will be a weak base. That makes this a strong acid. Okay. Now we can put them in order, strongest to weakest. What's the strongest base in this group? Oh, excuse me. That's kind of confusing because A minus is derived from a weak acid. If we say this is weak, then this one would be strong. Okay, so we're mixing apples and oranges here. The strongest base is going to be this one, from strongest to weakest. So this is the strongest base. The weakest base is going to be this one. because it comes from a strong acid. And water would have to go in the middle. There we go. Okay, acetic acid and hydrocyanic acid are both weak acids. Acetic acid is a stronger acid than hydrocyanic acid. So we write out our equations, C2H3O2, and we're going to keep it simple. C2H3O2 minus, and then hydrocyanic acid. Okay. If this one is weaker than that one, this one's stronger, this one's weaker. Okay. So this would produce as a weak acid. This is weak, and this is weak. It's going to produce a strong base, both of them. But what's the relative strength? Well, if this is a stronger acid than that one, this will produce a weaker base. So, acetic acid is stronger acid than HCl. So, arrange them in order, weakest to strongest bases, weakest to strongest bases. All right, so we have Cn minus is a stronger base than C2H3O2. Right. We know that the weakest base in there is going to be, weakest would be chloride. That's the weakest one. Then we have a relationship between these two, where Cn minus is the stronger of the two, C2H3O2 minus, and maybe water goes here. I'm not sure where water would go. Let's try to reason this. No? Oh, next slide. Oh, we're going to get some more information here. The kW for water, what does that mean? I mentioned that earlier, kW. Well, we have to look at water dissociation in terms of what it produces. This is a liquid. These are in aqueous solution, so kW expression is only those two terms. We don't use pure liquids. Right? And that's equal to 1 times 10 to the minus 14. All right. That's the equilibrium constant for water. Let's see. Bases from weakest to strongest. So chloride is the weakest. Then we put water, and then these acetate, and then cyanide is the strongest. Now, the only way to be sure about this one is to know what their relative equilibrium constants are. Then we can get a better idea of their absolute relationship, but this is a good guess. Okay. Now, I wrote it out this way, but in fact, what happens in solution is that water reacts with water to produce hydronium plus hydroxyl. Okay, That's the actual reaction, chemical reaction of pure water. So sometimes we say water is amphoteric. Ampho is Greek for both. That means water can either be an acid or a base. We can arbitrarily say this one's an acid and this one's a base. So this one loses a proton. This one loses a proton. This one accepts the proton. And accepting the proton, this is a conjugate acid. This is a conjugate base. All right. Now, if the K is 10 to the minus 14, that very small number, what does that mean? That means that the reaction is very slightly to the right and mostly to the left, right? In pure water, most of the water in there is in its molecular form, like this. And you only have just a tiny amount of those two ions. All right, so there's our expression, simplified expression. Now, at 25 degrees, it's important that you remember that no matter what else we put into the water, this reaction is still happening. Whenever two water molecules meet each other, they can exchange protons. If we put acetic acid in there, acetic acid will participate in a reaction with water, but the water can still react with itself, one water molecule with another one. So just because we put something else in water doesn't mean that that reaction goes away. It's still there. It may not be the dominant reaction, but it still happens. Okay. So I'm going to leave that part up there, and let's just erase this part right here. So when we have a solution of pure water, how did we get to this 10 to the minus 14? Well, this hydrogen came from one water molecule. This one came from another water molecule. But they have to be equal in concentration, don't they? In order for this reaction to proceed, 1 to 1. So that means this must have been 10 to the minus 7th molar and 10 to the minus 7th molar. When the hydrogen ion concentration is equal to the hydroxyl concentration, and under these conditions, this is 25 degrees C. If we change the temperature, then that will change, but it will still be equal. So when hydrogen ions are equal to hydroxyl ions, we have what's called a neutral solution. It's neither acidic nor basic. If we modify the solution so that hydrogen ions at equilibrium are greater than hydroxyl ions, then we have an acidic solution. How do we do that? The easiest way is just to add some acid to it. You know, add some hydrochloric acid. That'll do it. The other possibility is hydrogen ion concentrations are less than hydroxyl ion concentration. And this is a basic solution. Now you'll notice that we're speaking in terms now of the Arrhenius model, where we're actually defining these values. But they are also derivable from Bronsted and Lowry. It's just a little more complicated. Okay, that's how we define neutral, acidic, and basic solutions. And the acidic solution is going to taste sour. Basic solution is going to taste bitter. If it's safe to taste, that is. Okay, in each case, this is just position. The K still is the equilibrium constant 1 times 10 to the minus 14. That hasn't changed. The equilibrium position has changed, but not the K. Okay. In an acidic aqueous solution, which statement below is correct? Well, I mentioned that at 25 degrees, pure water would give you 10 to the minus 7, 10 minus 7. So if this is true, 1 times 10 to the minus 14 equals hydrogen ion concentration times hydroxyl ion concentration. If the acidic solution, if this one is greater than that one, and this is a constant, then if this one, this is an inverse relationship. If this one increases to exceed that one must decrease. We have no other choice. So, for example, if this were 10 to the minus 6 molar, right, that would be greater than 10 to the minus 7th, wouldn't it? This one would have to be 10 to the minus 8 to give us that value right there. Okay? So the hydrogen ion concentration would have to be greater than 10 to the minus 7th molar to be acidic. Okay. In an aqueous solution in which hydroxyls are 2 times 10 to the minus 8, the hydrogen ion concentration is what? Well, what we would do is we would substitute, right? And this is an equation. So if we know one of these values, we can calculate the other one. 2 times 10 to the minus 10 molar. So that means hydrogen ion concentration would be 1 times 10 to the minus 14 divided by 2 times 10 to the minus 10. Right? We can put that in our calculator, or we can do it longhand. Right? This part is 0.5, right? 1/2. This part is 14 plus 10, or 10 to the minus 4. So let's fix this up. It's 5 times 10 to the minus 5. That's the hydrogen ion concentration. Well, what does that mean? Well, if this is greater than 10 to the minus 7, it means the solution is acidic. That means it's B, C, or D, and C is the only one that works. Right, there we go. Solve, solve, solve. There you go. The solution is acidic, and the concentration is 5 times 10 to the minus 5 molar. Now, to the pH scale. Why would we want to complicate it any further? Well, actually, pH doesn't complicate, it simplifies. And it's based upon the work of a Swedish chemist, I believe, Sorensen. Sorensen was working with acidic and basic solutions, and he was tired of using scientific notation for all of his concentrations. He wanted to simplify things, and he hit upon the possibility of doing a logarithmic transformation of the concentration of hydrogen ions. Well, if we take, say, in a neutral solution, we would have 1 times 10 to the minus 7 molar hydrogen ion concentration. Okay? So Sorensen said, why don't we take the log of that? Right? We take the log of this, and the log of that, what do you get? Well, remember what logarithms are. Logarithm, and this is base 10, this will be the logarithm of the hydrogen ion concentration is the power of 10 that equals that value. So that means the log of this value is minus 7. Right? Well, Sorensen didn't much care for negative signs either, because they can get lost. If we can develop a system that only has positive signs for most values, then that's a good thing. So he just put a negative right here, negative right there. And now, if the hydrogen ion concentration is 1 times 10 minus 7, the pH is 7. All right. And by the way, significant figures. When we do a logarithmic transformation, and this is true for any log transform, it's not just for pH. But if you have two significant figures here, you will have 2 decimal places in your logarithm. All right, that's pH. So what does that mean if we increase the concentration of hydrogen ions? Say now, instead, we have hydrogen ion concentrations of 1 times 10 to the minus 6 molar, right? We went up by a factor of 10, 1 order of magnitude. What's the negative log of that value? The negative log, or the pH, would be 6. Okay? So what does that mean? This is more acidic than that. In fact, this is neutral. This is acidic. So as the concentration of hydrogen ions goes up, the pH goes down. So pH 3 is stronger than pH 6. But how many times stronger? Well, if this is 10 to the minus 6, this would be 10 to the minus 3. Right? So it's 10 to the third power difference. That's 1,000 times. pH of 3 is 1,000 times stronger than pH of 6 in terms of hydrogen ion concentration. That's simply an artifact of a logarithmic transformation. Now we can take logarithm of anything. Suppose we have a 1 molar solution. Let's make a how about 10 molar? 10 molar in hydrogen ions. Negative log of 10, base 10 of 10 molar equals negative 1. Right? Because the power of that one is 1, and 10 to what power equals 10? With a negative sign. So a negative times 1 is 1. So in this case, the pH is a negative value. Right? It's just a logarithmic transformation. It's a formula. And there's your significant figures description. Now, what is the normal pH range of interest to chemists? We generally don't go into the negatives. If we get that low, we use concentrations. So we typically have a pH range up between, let's see, let's make room here. We don't need this anymore. If we put pH on a scale, and this is neutral, right? That would be pH 7. And we want more acidic on this side. and we want basic on this side, then the numbers have to get smaller. 6, 5, 4, 3, 2. And that's typically where we stop. You can go lower if you want. This side would be 8, 9, 10, 11. We'll even go up to 12. So the typical range is between 2 and 12. 7's neutral. Anything greater than 7, basic. Anything less than 7 is acidic. Okay. And here's some examples of chemicals and foods and such physiological pHs. Blood tends to be just slightly basic. And that, when you're talking about some of these materials, you're talking about buffered solutions, those that where the pH does not change very much. And it's designed that way. Your blood is buffered at a pH between 7.35, 7.45. Very narrow range. If it gets outside that range, you can have acidosis here, you can have alkalosis there, and those are dangerous conditions. Various diseases or metabolic problems can cause that. The one that comes to mind is diabetes. Diabetes generally go this way, acidosis. And then milk is slightly acidic. Okay? Ammonia, household ammonia cleaner is very, very high pH. Sodium hydroxide, 1 molar sodium hydroxide is very high. In fact, it's outside our range. It's up to 14. Vinegar is around 3.4 thereabouts. Vinegar is 5% acetic acid. Lemon juice is a little stronger acidic. Stomach acid ranges between 1 and 2 pH, and it's predominantly hydrochloric acid. Now, it varies that much depending on what you're eating. Right? It's going to be a higher pH when you're not eating anything because you don't want to damage your stomach, right? But when you have food in your stomach, you want more acid to help digest the food. So your stomach produces more acid when you eat. And some foods produce more acid than others. They come along with lots of acid, like tomato-based products, like spaghetti sauce. Will drive your pH down around 1. And then 1 molar hydrochloric acid is 0. All right. So let's see if we can calculate the pH for each one of these. Okay. I'm going to leave that scale up there for now. And we'll do 1 times 10 to the minus 4th. Hydrogen ions, concentration, 1 times 10 to the minus 4. So what's the pH there? If we take the negative log, then remember logarithms. I'm going to do this whole thing out. Negative log of 1.0 times 10 to the minus 4. So what's the rule in logarithms? If you if you take the log of a product, right? You take the log of A times B. That's equal to the log of A plus the log of B. Right? That's a logarithm rule. So that would be the negative log of 1.0 plus the negative log of 10 to the minus 14. Well, if we follow the trend, right, follow the rules, what power of 10 gives you 1? 0. 10 to the 0 is 1. So this would be 0 plus, and this would be minus 14 times a minus. So that would be a minus 14, And that would be equal to, oh, excuse me, not 14. My mistake. That's 4. This would be 4. For pH. And I will caution you, this is pH. That's not pH. That's not pH, right? Any of my students that give me pH as this or that or even this, any of these are false. And they will get you a nice big red X on that part of the paper. Okay, so the value here is 4. Actually, it should be 4.00 because you have 2 significant figures here. How about what's the pH of 0.040 molar hydroxyl? Right? This one's a little more complicated. Because we've got hydroxyl concentration, not hydrogen ion concentration. So we have to go back to Kw equals 1 times 10 to the minus 14 equals hydrogen ions times hydroxyls, which is 0.040. There we go. So hydrogen ion concentration equals 1 times 10 to the minus 14 divided by 0.040. I want to use my calculator for this one. Okay. 1 exponent, negative 14 divided by 0.040. So this is 2.5 times 10 to the minus 13. So now the pH is equal to the negative log of 2.5 times 10 to the minus 13. I'll just take the log and then change the sign. And this is 12.6. Actually, 2 significant figures, 12.60 pH. There's the hydrogen ion concentration, and then 12.60. Okay. Now we're going to go backwards. Suppose you have a solution with pH 5.85. And you want to find out what's the hydrogen ion concentration of that solution. What you need is to say, what is that equal to? That's equal to the negative log of the hydrogen ion concentration. And then solve that equation for the hydrogen ion concentration. Well, we have to put the negative over here. So it's negative 0.85 equals log of hydrogen ion concentration. Okay? 2 ways to approach this. The hydrogen ion concentration then will be the anti-log of negative 5.85. Now, that may not mean anything to you. So a more efficient way would be to say, all right, what's the definition of a logarithm? This value is the power of that 10. So 10 to the minus 5.85 is that value. Okay? That's what antilog is. And on most calculators, you'll have a key for log, which is the common logarithm. And right above it, you have a shift to 10 to the x. That's the one you use for this. So if I put in 5.85 and change the sign, and then hit my 10 to the x key, I will get, let's say, two decimals is two significant figures. 1.4 times 10 to the minus sixth molar. That's the hydrogen ion concentration. We went overboard there. It should only be two significant figures. All right. We've shown you the long way around. Like if you're given hydroxyl ion concentration, what's the pH? We can do that. But there's a simpler way to do it. Much less prone to error. I'm going to get rid of this too. It takes the concept of pH, which is simply a logarithmic transformation, and applies that same idea to the hydroxyl ion concentration. Okay? So if pH is equal to the negative log of the hydrogen ion concentration, POH is the negative log of the hydroxyl ion concentration. All right. One step further. If we have KW for water, and we take the negative log of that K value, that's pKW. All right. It's just the logarithm. So if we go back to our original equation, where we have the ionization constant for water, and that's equal to H plus and OH minus, what if we take the negative log of that entire expression? If we do that, and this negative log here is pKW, and remember, the log of A times B is the same as the log of A plus the log of B. So this would be the negative log of hydrogen ion concentrations plus the negative log of hydroxyl concentrations. And there's your expression. But what did we leave out? We left out the actual value times 10 to the minus 14. What if you take the negative log of that? What's the negative log of 10 to the minus 14? Is 14. Okay. So if we have a hydroxyl ion concentration and we want to know the pH, calculate the POH, subtract it from 14, and you got the pH. Or if you want to know the POH, take for A, 1 times 10 to the minus 4 is hydrogen ions, right? So that pH would be equal to 14, right? Oh, 4. Why do I keep doing that? That's 4. There we go. Now the POH is equal to 14 minus 4 equals 10. So that first one is POH is 10. And POH for 0.040 is simply the negative log of that value, which is 1.4. Okay. All right. That makes things a whole lot simpler. So what's the hydroxide ion concentration for a solution that's pH 5.85? Let's make some more room here. We know that the pH is 5.85. pH equals 5.85. And the question is, what's the hydroxide ion concentration? We could convert this to hydrogen ion concentration and put it into the K formula, or we can say POH equals 14 minus 5.85, which is 5, 1, 5, 8. Is that right? 8, 10, 10, 14. That's right. This is POH. So pH, excuse me, this is pH. So the hydrogen ion concentration then would be 10 to the minus 8.15. Oh, I'm sorry. This is POH. OH minus. There we go. And that's equal to 10 to the minus 8.15. 7.08 times 10 to the minus 9. Okay. Calculating the pH of strong acid solutions. Okay. What we're going to get here is something that's extremely low, even sometimes negative. Complete dissociation. So if you have 2 molar hydrochloric acid, you can assume that the hydrogen ion concentration is also 2 molar. All right. So that's your value, minus 0.30. Okay. Sorensen wouldn't have used these values. He wasn't working in those pH ranges. So normal range, I said 2 to 12. Actually, we generally, well, you can work from 2 to 12 easily, but electrodes, pH meters with electrodes where we actually measure the pH directly, are generally inaccurate outside the range of 2.5 to 10.5. And if you know you're going to be outside that range, you need a special electrode. Otherwise, you introduce significant electrical error to your signal. All right. This solution is 2 times 10 to the minus third. What's its pH? If it's hydrochloric acid, you assume that it's 2 times 10 to the minus third molar hydrogen ions. And then you apply the equation, and our pH is 2.7. What if we have a pH that's extremely low? So what's the relative concentration of hydrogen chloride versus the, remember I said water is always undergoing that amphoteric reaction. So if we put hydrochloric acid in there, if we don't put enough, then the water is still dominant. So if we're saying the hydrogen ion concentration according to this calculation is 1.5 times 10 to the minus 11th, that's 4 orders of magnitude weaker than pure water. So the pH is still going to be 7. All right. It doesn't matter what you calculate with that value. pH is still 7. All right. What's the pH of nitric acid at this concentration? And nitric is a strong acid, so we can assume that that nitric is completely dissociated. Is there an error there? 1 times 10 minus 7 molar. Oh, water is 1 times 10 minus 7, but pH, the nitric acid is 10 to the minus 2, so yeah, it's dominant. That was the point. So we go ahead and use the concentration of hydrogen ions as given by the nitric acid concentration. And yes, the nitric is dominant in this case. Now I want to say a little bit about buffered solutions. Buffered solutions in chemistry are those solutions that are constructed in such a way that the pH will not change very much, very, very slightly, if we add an acid to it or a base to it. So how do we do that? We do it most often, not always, but most often, with a weak acid in combination with its conjugate base. So a good example is acetic acid, right? In the simplified version, this is what it would look like. So this is a weak acid, and this is a strong conjugate base. Strong base. This is a weak acid. Okay. If we have the right concentration and combination of these two, you have to have some of this and some of that in solution. If this is the case, then what happens when you add acid to the base, acid to the solution? If you add acid, what's going to look for? I mean, all of this is in the same solution. So what's going to happen? If you add acid, you're adding hydrogen ion. Right? They're going to react with the acetate ion, which is a very strong base. So it's going to pick up those hydrogen ions, and it's going to shift the equation this direction, right? Back over here. Until when? Until equilibrium is reestablished. That's according to Le Chatelier. Reestablish a new equilibrium position, which, since we have consumed much of the hydrogen ions, we don't unbalance this hydrogen concentration by much. Now, it won't be all because this is equilibrium. So we'll have a few extra hydrogens, but not many. That means the pH will be fairly stable. The pH will drop just slightly. It may even be undetectable. What if we add hydroxyls? Well, the hydroxyl is derived from water. Right? This is a very weak acid. This is an extremely strong base. Right? So we can look at it in two different ways. Right? This strong base can either pick up these hydrogens, and that will shift the equilibrium this way to replace those hydrogens and keep the system in equilibrium and the pH fairly constant. Or this hydroxyl can take a hydrogen from that species, and that produces this. Right? That produces this without the hydrogen over here. So what happens? Well, in that case, if we produce more of this, it's going to react with some of its hydrogens and shift back over here. So either way, you get an equilibrium position that is fairly stable with respect to pH. Now, the other possibility is we can buffer our solution with a weak base as well. And that's what we're looking at here. Ammonia is a weak base. So let's change that part, and let's change this part here. Ammonia. And I'm going to keep it chemically pure. That's what happens. This is NH4 plus, and this is OH minus. That's a very strong base. Right? And this is a weak base. That makes this a strong acid. Okay. So now what happens? We're going to make this solution with ammonia and ammonium chloride. In this case, chloride is a spectator. We're adding this and this together in the same solution. We need some of both. So once we have the right combination, what happens if we add sodium hydroxide? What is sodium hydroxide going to react with? Well, sodium hydroxide, the sodium is another spectator. So the hydroxide is the important part. If we add hydroxide, it's going to shift the reaction back this way, right? And use up some of that hydroxide so it's not as basic as it was before. So sodium hydroxide plus the strong acid, right? It's going to pick up some of these hydrogen ions. So that would be B. Best answer is B. Sodium hydroxide is going to combine with these and keep this one fairly constant. All right. So that is, for this course, that's all we're going to say about acids, bases, and pH.